This is part 4 of the series Limits, and in the last part we looked at employing the basic properties of limits to evaluate limits. I'm going to begin this part by looking at limits we have to evaluate analytically. So let's take a look at 3 basic limits here. The first one up here, we want the limit as x approaches 1 of this rational function. Now, as we can see, this has a little bit of a problem because at x equals 1, the denominator becomes 0. But hopefully you'll notice here that this numerator is the difference of 2 cubes. So what we'll want to do is expand that and see if we have any cancellation opportunities, because we've got to get rid of this problem with the x minus 1 in the denominator. So this is the equivalent of the limit as x approaches 1 of. Now we take the cube root of the first term, that sign, the cube root of the second term. Then to expand it, we take the square of the first term, the opposite sign, this times this, so that's x, and the square of the third term, and it's always going to be positive. And that's over x minus 1. Now clearly we see we have a cancellation opportunity here. And this limit we can evaluate directly. Now directly substituting the 1 for x in here, we get 1 squared plus 1 plus 1, which is 1 plus 1 plus 1, which is, of course, 3. All right, let's go down to this one. Here we have a similar problem. We have an x plus 3 in the denominator. If we put a negative 3 in here, the denominator becomes 0. Well, here we have a quadratic, so let's see if there's any way we can factor this guy out. So that quadratic is x, and that's a negative sign, so it's plus and minus, and 3 and 2, x squared minus 2x plus 3x, that gives us the positive x minus 6. So there we go, over x plus 3, and we have the limit as x approaches negative 3. Well, these cancel out, and we can do the direct substitution into this piece here. So we have negative 3 minus 2, which is negative 5. So this limit is negative 5. Now, there's an alternative here. Let's just say, for the sake of discussion, that you didn't recognize that this could be factored. Let's just assume that. But you see that this is a quotient. And so what you could do is simply carry out the division here. So because this is a binomial down here, we can use that factor. So negative 3, and we have 1, 1, and negative 6. So using synthetic division, we have negative 3, and we add, and we add, and here we have x minus 2. So we'd have gotten to the same thing, and we would have taken the limit of this expression here. So either way, whether you can see that this is factored, use the quadratic formula, or in the case where, and very often this will be the case, where this is not easily or even possible to factor, this is the most expeditious way to find your result that you can direct substitute in to find your limit. But these are just some simple analytical techniques. Let's go look at this third one over here. In this case, we have a slightly different issue. Here, there's nothing in the denominator that's going to cancel out directly here. So we're going to have to somehow manipulate this into some form that may perhaps give us some sort of cancellation opportunity. Now, when you're dealing with radicals, one of the things you always want to think about is the idea of conjugates. And if you remember from your days of imaginary numbers, and you looked at complex conjugates, rational functions also have conjugates here. And the conjugate of this would be the square root of x plus 1 plus 1. And what I want to do is I want to multiply this by some form of 1. And that form of 1 is going to be the square root of x plus 1 over x square root of x plus 1 plus 1. Now by multiplying through here, the hope is that we're going to develop some sort of expression that will get rid of this problem x in the denominator. Let's see if it does. When we multiply this times this, what we're doing at this point is we're multiplying this expression by this. And so what we want to do is we want to multiply every term here by every term here. And the same thing here, this by each one of these terms. So this term times this term is simply x plus 1. This times this is 1 times that, which is the square root of x plus 1. And this times this is minus the square root of x plus 1. That is the beauty of conjugates. Every time you multiply a conjugate, multiply some value by its conjugate, you're going to eliminate that middle term. And then this times this is negative 1. So these terms are going to go away. And then this times this is simply x times the square root of x plus 1 plus 1. Now as you can see here, this positive 1 and this negative 1 cancel out. So these are going to go away. And now we have x divided by x here. And so this x is going to cancel this x out. So what we have left is 1 over the square root of x plus 1 plus 1. Now in this case, since this expression is equivalent to this one because of this manipulation, we can do our direct substitution here. And we end up getting 1 over the square root of 0 plus 1 plus 1, which is 1 over 2. The key things to remember when you're evaluating limits is that the limit is not what the value of the function is at that c value. It is what is the function approaching. That is the critical thing, because your knee-jerk reaction is going to be to look at these, plug in a 1, say, oh, that's not possible, so the limit doesn't exist. Be very, very careful with these. You must do some manipulations to ensure that there's no way to manipulate out the flaw, and you can actually find what this function is approaching as it approaches that value. All right. Now we're going to look at a couple of special trigonometric limits and a new theorem. So let's take a look at that. This theorem is called the squeeze theorem, and it sounds a little silly, but its name is appropriate. And the idea is that, let's say that you have two functions, f and h, and those functions have the same limit at some c value. So the limit of f of x as x approaches c is some L value here, and the limit of h of x as x approaches c is the same L value. Now let's say that you have a third function, g of x, that is always between f and h. That is, given that f of x is less than or equal to g of x, which is less than or equal to h of x, for all x on an open interval containing c, again, except possibly at c itself, because the functions don't have to be defined at the limit value, then the theorem states that if this condition is held, and if the limit of f is equal to the limit of h as x approaches c, if this limit is the same, then the limit of g of x at that same c value must be equivalent to the limit of f and h at that value. Now, the value of the squeeze theorem is that often you will encounter functions that can't be evaluated analytically, in which case the challenge is going to be to find bounding functions, f and h, such that we can evaluate what their limits are at a target value. And assuming we can prove that g is between f and h, then we know that if the limit of this is equal to the limit of this, and this is always between these two, then the limit of this at that value has to be the same as these limits. So let's put this into practice using two special trigonometric limits. Now let's take this first limit. We have the limit as x approaches 0 of sine x over x. And that limit is actually equal to 1. Now, as you can tell, we can't evaluate this directly because of that x in the denominator. And there's no real way to manipulate out that x in the denominator. So there has to be an alternate way to break this down in order to be able to evaluate this limit so that we can come up with this final result. And that is using the squeeze theorem. To use the squeeze theorem, we're going to have to come up with some functions that bound this function. So let's start out by looking at a unit circle with some areas superimposed on it. So in this unit circle, we have drawn a large triangle here. We have an area of a sector that you can see here. So this is the area of a sector. And then we have a smaller triangle inside. So clearly you can see that the area of this big triangle is going to be larger than the area of this sector, which is going to be larger than the area of this small triangle. So we're going to be using these areas to generate our bounding functions. So let's go and take a look at those areas. The area of this big triangle is 1/2 base times height. 1/2, 1 is just 1/2, and the base is 1 times height, which is tan theta, because this y value is tan theta, taking o's away. So that's the area of this triangle. The area of this sector is given by this proportion. Area of sector is the area of the circle as central angle is to 2 pi. And if we simplify this out, the area of the sector becomes theta over 2. And that's the area of the sector. And of course, because this is greater than this, greater than or equal to this, we have this first instance of our bounding functions. And the third smallest triangle, 1/2 base times height. Well, this height is this sine value here, sine theta. So 1/2 base, 1/2, 1 is 1/2, times sine theta is sine theta over 2. We're going to need to manipulate these functions so that this central function, this central term here, is going to look like this ultimately. Now the way we do that is by multiplying each one of these areas by 2 over sine theta. So let's take a look at what that result. When we multiply this by 2 over sine theta, we get 1 over cos theta. When we multiply this by 2 over sine theta, the 2's cancel out. We get theta over sine theta. And this is simply 1 on that side. Now in order to turn this into this expression, we simply take the reciprocal. And if we take the reciprocal of each one of these terms, we have to change this inequality. So here we have cos theta is less than or equal to sine theta over theta, which is less than or equal to 1. Now that's all we have left to do is evaluate these two limits. And so over here, we have the limit as theta approaches 0 of cos theta. As this angle approaches 0, this value is 1. So cosine is the x value, so that's 1. The limit as theta approaches 0 of 1, that's just a constant, so it's just 1. So this limit and this limit are equal, therefore the limit as theta approaches 0 of this quantity must also equal the same value, which is 1. And that's where this comes from. Now the idea of this is very similar in nature. We're not going to go through that proof, but the idea of these two is very important because these can't be easily evaluated analytically, and we use the squeeze theorem for this one. So the limit as x approaches 0 of sine x over x is 1, and the limit as x approaches 0 of 1 minus cos x over x is 0. And this also works, by the way, the limit as x approaches 0 of x over sine x is also equal to 1. That's going to be an important artifact later on. So in the next part, we're going to go ahead and look at a few trigonometric limits. And so I will talk to you in the next part.